Yeah. So, we have seen that Hagen-poiseuille equation, how we have developed in a pipe, in a pipe for a fluid which is incompressible and under steady state and laminar flow. This, there is no end effect, there is no velocity development in along the flow of the fluid that we have seen, right. Velocity profile was not also developed in the flow of the fluid along the pipe. So, this we have already found out. Now, one more thing we had said earlier that you can utilize the equation of motion or these equations which we developed known as the Navier-Stokes equations. From the Navier-Stokes equation also this you can find out and develop. So, we will do this today also again, right. So, for that let us go to that situation that we have taken this fluid, we have taken the shell momentum balance we have done, right. So, here we will do with the Navier-Stokes equation. If you remember the Navier-Stokes equation of the r, theta and z component, r, theta, z component equations we had used. So, similar to that we will use also here r, theta, z component, right. So, let us take, in that case we know that V r is equals to V theta is equals to 0 and del V z del z is equals to 0, right. V r V theta V z, since that was r theta z, right. So, here also we take r theta instead of x as z, right, instead of x as z. So, r theta z if we take, so V r is equals to V theta is equals to 0, because what we are supposed to do, we are supposed to find out that V is flowing like this, right. V is flowing like that. So, it is V z which is flowing like that and V r is this. So, this V r and V theta is that which is like that. So, V theta will be taking, since the flow we assumed is laminar, we assume steady state, we assume no end effect, we assume flow is fully developed, and also we assume there is no velocity profile along the flow of the fluid. So, we assumed all these. So, in this case, knowing these conditions, the conditions of the flow, this is called the problem description. So, from the problem description, we can tell V r is equal to V theta is equals to 0, that is V r is 0 and V theta is 0, there is no velocity component, right. In the r direction, there is no theta component V theta in the theta direction, this is 0 and V del V z del z, there is no flow in the direction of the flow, there is no velocity profile, that del V z del z is also 0. So, in this case, if we assume all these three, then we can write from the Navier-Stokes equation. If you remember that the first equation, second equation and third equation, if we take the if we take this equation, that mu into 1 by r del r into r del v z del r, right. This is minus del p del z, this is equals to 0, right. Since it is horizontal, so rho gz we can tell it to be equals to 0, right. So, we can write 1 by r, this is the from the Navier-Stokes equation, right, and in the z that r theta z, this is the z1 del r of r del v z del r, right. So, 1 by r, then 1 by r del r of r del v z del r, right. This is equals to 1 by mu del p del z. So, this we have taken to the other side, this del p del z. This is equals to, we can write del r of r del v z del r, right. This is equals to r by mu into del p del z, right. So, on first integration we can write r del v z del r is equals to 1 by mu del p del z into r square by 2 plus C 1. Why you have not taken in del p del z in the integral part? Because del p and del z they can be said to be given, right. So, del p means p in minus p out, that is del p, and del z is nothing but the length. So, once we know the length, that is for a given length, right, for a given flow, we know del p, we know del z. So, del p del z is known. So, that is why it is not going into the integration. So, we can write r del v z del r is equals to, on the first integration, 1 by mu del p del z r square by 2, right, plus C 1, right. So, this on first integration, and we can also say on the rearrangement of this as del v z del r is equals to del v z del r is equals to 1 by mu del p del z, right, and this r goes there. So, it is r by 2 plus C 1 by r, right. At r is equals to, now the boundary condition which we can apply at r is equals to 0, del v z del r is also equals to 0, right. At r is equals to 0, that is this point, right. At r is equals to 0, del v z del r, that is also equals to 0. Therefore, we can write C 1 is nothing but is equals to 0. At r is equals to 0, del v z del r is 0. So, C 1 is also equals to 0, r is equals to 0, this goes out, right. So, that also goes there. So, we can write that C 1 is equals to 0, and then we can also say that del v z del z is equals to 1 by mu del p del z into r by 2, since C1 was equals to 0. On second integration, we can write Vz is equals to 1 by mu del p 1 by mu del p del z, that is constant, into r square by 4 plus C2. Now, we can put the second boundary condition. Second boundary condition is what? At r is equals to capital R, Vz is equals to 0, right. If that be true, at r is equals to capital R, Vz becomes equals to 0, then C2 becomes equals to minus 1 by mu into del p del z, right, into r square by 4, right. Therefore, we can write Vz is equals to 1 by 4 mu, right, into del p del z, right, into r square minus small r square, capital R square minus small r square, right. C2 is this, right. 1 by 4 is this is with a negative, right, because that is negative. So, this can be written 1 by 4 mu del p del z, right, into r square minus capital R square, right. So, at r is equals to 0, we can write Bz is equals to minus 1 by 4 mu del p del z into r square. At r is equals to 0, right. This minus remains, Vz is equals to minus 1 by 4 mu del p del z r square, right. Now, we can say that Vz is equals to nothing but P in minus P out, right, into r square by 4 mu into L, right, which is nothing but V max. So, Vz is P in, how we have taken this minus in has become this delta P. Again, any delta P is generally out minus in, right. Anything delta is higher minus lower, but that is out exit minus inlet. So, in this case, since we are taking P in minus P out as the delta P, so this negative goes in there and this becomes P in minus P out by 4 mu L into r square, that is nothing but V max, right. Or we can write Vz is equals to V max, right, times rather 1 minus r by r whole square, right. Vz is nothing but V max 1 by 1 minus r by r square. This is what we have done in the flow of fluid in pipe, right. This we have done earlier, and with the help of Navier-Stokes equation, you have seen that you can also do the same thing for the pipe flow, and you can find out the velocity distribution in the pipe, right. Then Vz is V max. So, how the velocity distribution comes in? This is the pipe, right. This is r. So, velocity is 0 at the pipe and Vz is maximum at r is equals to 0. So, if this is the maximum, so then this will have a velocity profile like this, right. So, this will be the velocity profile in the pipe, right. So, now here you see in the previous class we had done with the shell momentum balance, and but in this present class we have also done the same thing with the help of the Navier-Stokes equation. Keep in mind, Navier-Stokes equation, if properly the terms can be identified, it properly you can substitute the values of the terms, then you can easily come to the solution, and for the flow of pipe we have done it carefully, right. So, we can say that like this. So, V average then can also be written as this is 1 by pi r square, that is the area into 2 pi r into dr V z, right, that is equals to minus r square by 8 mu delta p over delta z, right, that is r square by 8 mu delta p by delta z, right. So, V then V z average into d z is equals to minus r square by 8 mu into d p, right, or V z average into L is equals to P in minus P out, there is delta P r square by 8 mu, or Z V z average is equals to P in minus P out, right, into d square by 32 mu L, and this is Hagen-poiseuille equation, right. So, this is Hagen-poiseuille's equation. So, the Hagen-poiseuille equation we have found out with both flow through pipe and flow in the flow through pipe with the shell momentum balance as well with the Navier-Stokes equation, right. Then Navier-Stokes equation again and again I am forcing on that Navier-Stokes equation, you do not have to remember the entire equations, is not possible to remember the entire equations, all the components, r component, theta component and z component. When you are solving, you must take that this Navier-Stokes equation in all the r component, theta component and z component, they are with you in the right form, and then you understand them in the proper way, and the moment you understand them in the proper way, you can figure out in most of the cases you will see that from the given problem you will figure out what are the velocity components, whether all three of them are active or some of them are active or some of them are nullified, or it can be taken as 0. So, if you can identify them, if you can put them, then you do accordingly and then find out whether this Navier-Stokes equation is applicable there or not, how it can be applied, what are the terms which are like in this case you have seen that Vr and V theta is 0, and we also have found out that V del Vz del Z, that is also 0. But these words or these terms we have said in setting the problem. You remember while setting the problem we have said that the velocity component in the flow of the direction of the flow of the fluid does not have any velocity profile. That means it is not having any velocity profile in the direction of the flow. That means del V z del z is 0, right. We also said and when you are integrating, finding out the integral constants, there what you are putting? You are putting the boundary conditions. Here we have put the boundary condition at r is equals to 0, that is the central point. At r is equals to 0, you have V z, which you have found out, right. V z is equals to max, V max, right, and at r is equals to capital R, that is at the surface or at the inner surface of the cylinder, right, where the fluid is clinging. If this is the surface and if this is the layer of the fluid, so it is clinging to that, as if the surface is moving, it is also moving, but if the surface is fixed, it is not also moving, right. So, that is called clinging. It is clinging to the surface, and that means the surface has the velocity 0. So, there r at capital R we have taken to be constant, at capital R to be velocity to be 0, and we have shown how the velocity profile has changed, right, in the along the radius, right. So, that we have shown that if this is the pipe and if this was the axis, then velocity here it was 0, it became maximum, and then this is nothing but a mirror image of this half. This half is the mirror image of this half. So, whatever was there, the same thing came out to be here, right. In many cases, that is why subsequently you will see, once if we for a symmetrical thing, if you do half of it, the rest of the things can be assumed to be the same, right. So, let us then, the next we will do when we will have other things, right. Most probably next we will be going for finding out the another thing, as from here it is appearing that this is clinging, right. The surface which is clinging to the wall is not moving, right. So, this is known as friction, right. So, one layer with the other layer with the other layer, they are having some friction. Otherwise, why P out and P in, there will be some difference. Why P in and P out, there will be some difference. Who is taking it? This is taken by that frictional force which is dragging or drag force one another. This we will do in the subsequent class. Okay? Thank you.